You check your phone for the time without even thinking about it. 100 times a day. You glance, you register the number, you move on. You assume time moves the same way for you as it does for everyone else on the planet. But the real answer is much stranger than that. Time is not one single river flowing through the universe at the same speed for everyone. It bends. It stretches. It slows down near heavy things and speeds up near light ones. And somewhere out in space there is an object so extreme that inside it, everything you think you know about time simply breaks apart. It is called a black hole. Not a hole in the way you imagine a hole. Not empty space. The opposite. A black hole is matter crushed so tightly, so densely, that its gravity becomes strong enough to trap light itself. Nothing that falls in ever comes back out. Not a signal. Not a beam. Not even the glow you would expect from something burning. How does something get pulled so tightly that light cannot escape it? The answer starts with a man sitting in a quiet room in 1915, working out equations by hand. His name was Albert Einstein. He was not thinking about black holes at all. He was trying to describe gravity in a completely new way. Not as a force pulling objects together, the way an apple falls to the ground. Instead, he described gravity as the bending of space and time itself. Mass tells space how to curve. Space tells objects how to move. It sounds abstract until you picture it simply. Imagine a stretched sheet of fabric. Place a bowling ball in the middle. The fabric sinks around it. Now roll a marble nearby. It does not travel in a straight line anymore. It curves toward the bowling ball, following the dent in the fabric. That dent is what gravity actually is. Not a pull. A curve. Now make the bowling ball heavier. And heavier again. At some point, the dent becomes so deep, so steep, that it stops looking like a curve and starts looking like a hole with no bottom. That is a black hole. A dent in space and time so extreme that nothing, not even light, can climb back out of it. Only months after Einstein published his equations, a German physicist named Karl Schwarzschild was serving on the front lines of the First World War. In the middle of that chaos, he solved Einstein's equations for a simple case, a single point of concentrated mass. His solution described exactly what would happen if enough mass collapsed into a small enough space. It predicted an edge, a boundary in space itself, past which nothing could return. Today we call that boundary the event horizon. Cross it, and you are not coming back. Not because of engine failure. Not because of distance. Because space itself is falling faster than light can travel outward. You would be running toward the exit on a treadmill moving backward faster than your legs could ever carry you forward. But here is where it gets strange for you personally. If you could somehow survive falling toward a black hole and watch a clock on your wrist while a friend watched you from a safe distance through a telescope, the two of you would disagree about how much time had passed. Not because either of you made a mistake, because time itself would be moving differently for each of you. To your friend far away, you would appear to slow down as you approach the edge. Your movements would stretch out. Your voice, if you were somehow broadcasting it, would drop lower and lower. You would seem to freeze, forever hovering just outside the boundary, never quite crossing it, fading slowly from view like a photograph left out in the sun. But from your own perspective, none of that would be happening. Your watch would tick normally. Your heartbeat would feel completely ordinary. You would cross the edge in what felt like an unremarkable moment, unaware that to anyone watching from outside, you had just seemed to stop existing. Whose time is correct? Both of you would be right. That is the part that breaks most people's intuition the first time they hear it. Time is not a fixed backdrop the universe plays out against. It is a measurement that depends on where you are standing and how fast you are moving. Gravity changes the rate at which time passes. The stronger the gravity, the slower time moves relative to someone farther away. This is not a theory sitting untested in a textbook. It has been measured. Clocks on GPS satellites run faster than clocks on the surface of the Earth because they sit farther from the planet's gravity. If engineers did not correct for that difference every single day, your phone's map would drift off by miles within hours. The bending of time by gravity is something you rely on quietly every time you check directions. In 2020, an astronomer named Andrea Ghez won the Nobel Prize in Physics for tracking the motion of stars orbiting an invisible object at the center of our own galaxy for nearly 3 decades. Those stars whipped around something unseen at extraordinary speeds, bending their paths exactly the way Einstein's equations predicted they would around an enormous hidden mass. That mass turned out to be a supermassive black hole, millions of times heavier than the Sun, sitting quietly at the center of the galaxy you live in right now. You are, at this very moment, orbiting a black hole. Not falling into one. Orbiting one, the way the Earth orbits the Sun, just at a much safer distance. Here is the twist most people never expect. Physicists still do not agree on what happens at the very center of a black hole, the point Schwarzschild's math predicted where all that mass gets crushed down to. The equations say the density becomes infinite. But infinity is usually a sign that the model has stopped describing reality and started describing the limits of the model itself. Something is missing. A black hole does not just challenge what you know about gravity. It marks the exact spot where physics itself runs out of answers. So why does any of this matter to you? Checking your phone for the time in an ordinary day that has nothing to do with space. Because the same lesson black holes teach on a cosmic scale is quietly true in your own life, just far too small to notice. Time already passes slightly differently for you than it does for someone living at a different altitude, moving at a different speed, standing closer to or farther from the Earth's own gravity. The difference is too tiny to matter to your calendar. But it is not zero. You have never experienced time as a fixed, universal constant. You only believed you did because the differences were too small to see. For decades, most scientists treated black holes as a strange mathematical curiosity, something the equations allowed but nature probably did not bother building. Even Einstein himself doubted they were real. He thought nature would find some way to avoid anything so extreme actually forming. It took another physicist, Roger Penrose, to prove mathematically in the 1960s that under the right conditions, collapse into a black hole was not just possible. It was unavoidable. Enough mass, packed tightly enough, and there would be no force in the universe strong enough to stop the collapse. Penrose later shared the Nobel Prize in Physics for that proof, decades after he first worked it out on paper. Still, proving something on paper is different from seeing it. For 100 years, nobody had an actual image of a black hole. Just equations, orbiting stars, and indirect clues. That changed in 2019, when a global network of telescopes, coordinated across the planet as a single project called the Event Horizon Telescope, finally captured a picture. Not of the black hole itself. You cannot photograph something that traps light. What the picture showed was the shadow, a dark circle surrounded by a glowing ring of superheated gas being pulled in at nearly the speed of light. It was the first time humanity had ever seen, with its own eyes, the edge of the place where time and space stop behaving the way you expect them to. Think about what that means for a moment. For your entire life, and for every life before yours, human beings looked up at the night sky and saw stars, planets, familiar points of light. Nobody saw the black holes. Not because they were rare. Scientists now believe nearly every large galaxy, including your own, has one of these objects sitting quietly at its center. You simply cannot see something that swallows the very light that would let you see it. That is worth sitting with. The most extreme objects in the universe are also the most invisible ones. The greatest distortions of time and space are hiding in plain sight, at the center of the galaxy you were born into, doing nothing to announce themselves. And that brings the story back to you, standing somewhere on the surface of a planet, orbiting a star, which is itself slowly orbiting one of these invisible giants. Every second you experience is shaped, in some small measurable way, by gravity you cannot feel and cannot see. Astronauts who spend months aboard the International Space Station return to Earth having aged, by a measurable fraction of a second, differently than the people who stayed behind. Not because their bodies work differently, because they spent months moving faster and sitting slightly farther from the Earth's gravity than everyone waiting for them at home. Their clocks, quite literally, told a different story of time than the clocks on the ground. You will never fall into a black hole. Almost certainly, nothing you do today will bring you within 1 trillion miles of one. But you already live inside the same rules that govern them. Time was never handed to you as a fixed, shared script that everyone reads at the same pace. It was always local, always personal, always shaped by exactly where you are standing and how fast you are moving through space, whether that space bends gently under the weight of a planet or collapses completely under the weight of a dying star. You check your phone for the time without even thinking about it, 100 times a day, but there was never really a single time to check. Only your version of it, moving at its own pace, in its own small curve of space, exactly like everything else in the universe around you.